this video, we're going to be talking about related rates word problems. So the math on these problems is just like the previous video. It's just we have a word problem to set up in order to get to the equation that we need. So the first thing we want to do is identify all the given quantities and quantities that we have to determine. You might make a sketch if it's appropriate, but you might want to make sure everything's labeled. You're going to write an equation which involves the variables whose rate of change are given or to be determined. Using the chain rule and implicit differentiation, we're going to take the derivative of both sides of the equation with respect to t, and then we can substitute all the known values back and solve for the required value. Now you must formulate a mathematical model based on the information and then solve for the required rate of change. So sometimes this is going to involve geometry formulas, sometimes it's going to involve triangles, all sorts of different things. You might use some trig like sine, cosine, and tangent. A lot of different places where you might get your formulas here. Now if there is some kind of weird geometry formula, anything other than the area of a circle or the area of a square or a triangle or the Pythagorean theorem, I would give you that on a test if you need it, but I do expect you to know those really basic things like areas of rectangles, areas of circles, again, the Pythagorean theorem and the SOHCAHTOA rules. So any of that is fair game, but anything else, if it was like the volume of a dodecahedron, of course, I'm not going to expect you to remember that. I would give you that formula. So let's take a look at a really simple example. This says the radius r of a circle is increasing at a rate of 4 centimeters per minute, and we want to find the rate of change of the area when r is equal to 8. So let's look at what we're given here. We are given that the radius of a circle is 8 centimeters, and we're given that the rate that it's increasing, dr over dt, because that would be the rate that the radius is increasing with respect to time, is going to be 4 centimeters per minute. Now notice that it said it was increasing, so if it's an increasing rate, that means dr over dt has to be positive. If it had said that that was decreasing at a rate of 4 centimeters per minute, we would set that to be a negative 4. So increasing or decreasing does determine the sign of that number. So of course r here is the radius in centimeters, and the other thing that we're looking at is area. So we're going to let A be the area, and this would be in centimeters squared. So the area of a circle, area is pi r squared, and what we want, the rate of change of the area, is dA over dt. So we want the rate of change of the area with respect to t. So I'm going to start just like always, and I'm going to take the derivative with respect to t of both sides. And I'm going to note that I have a mismatched variable. These will always have mismatched variables when you're working on these types of problems. This just gives me dA over dt because the derivative of a would be 1, and then you have to multiply that by a prime. And this one I would have 2 pi r, and then I would have to multiply by dr over dt. Because pi is a constant, you bring down the 2 and then you subtract 1 from the exponent. So that is my derivative. Now I want to find dA over dt. So when r is equal to 8 and dr over dt is equal to 4, dA over dt is going to be 2 pi times 8 times 4. So that ends up being 64 pi, and that's going to be centimeters squared per minute. So that is my answer. Now, unless you were told specifically to round to so many decimal places, you want to leave that as 64 pi. That is considered an exact answer. A classic kind of related rates problem involves a triangle. So this is what one of those problems might look like. A ladder 25 feet long is leaning against the wall of a house. The base of the ladder is pulled away from the wall at 2 feet per second. How fast is the top of the ladder moving down the wall when its base is 15 feet from the wall? So whenever you end up with one of these ladder situations or anything where you think a triangle might be involved, it's a good idea to go ahead and draw a picture. It doesn't have to be beautiful, I'm not an artist, but it does have to at least kind of give you an idea of where the different pieces of the problem are in relation to each other. So this is going to be the wall of my house, and hopefully it is constructed in such a way that it is at a 90-degree angle with the ground, so we're going to assume that. And this is going to be the ladder that is leaning up against my house. So I've got a ladder, And we are told that the ladder is 25 feet long. So this is a right triangle, and we're talking about the sides of a right triangle. So I'm going to assume that we're going to use the Pythagorean theorem. And that is a squared plus b squared equals c squared. Now again, this is something I do expect you to know. So the problem is telling us that the ladder is 25 feet long, and that is the side that's opposite the right angle. So that's my hypotenuse. So c is 25. The base of the ladder is pulled away from the wall at 2 feet per second. So this is the speed at which this is being pulled away from the wall. So this is the base of my ladder right here. And then I'm going to pull it away from the wall, meaning this distance is getting bigger. So if this is A, then dA over dt is going to be a positive 2 feet per second. It also asks us how fast is the top of the ladder moving down the wall when its base is 15 feet from the wall. So we also know that A is 15, that's this distance. And we can conclude that the distance, or that the rate that we're looking for, we want to know how fast the top of the ladder is moving down the wall. That's how quickly is this side shrinking. So we're looking for dB over dt if this side is B, and we don't know the value of B yet. So this is our big question mark. Now we can find B pretty easily using the Pythagorean theorem. We know that A is 15, so that'd be 15 squared plus whatever B is has to be equal to C squared. So that tells me that 225 plus B squared has to be 625. And if I solve for that, I get that B squared is 400, or B is 20. And again, we're talking about the length of something here, so we don't have to worry about signs. So I know that B is equal to 20, and I can use that in my problem. So I'm going to take the derivative. I always have to take the derivative. The derivative with respect to t of a squared plus b squared is going to be the derivative with respect to t of c squared. So if I split that up, I get the derivative with respect to t of a squared plus the derivative with respect to t of b squared equals the derivative with respect to t of c squared. And that derivative is going to give me 2a dA over dt plus 2b dB over dt equals 2c times dC over dt. So we have three different rates here. Now you'll notice we're looking for dB over dt. That's our unknown. We have A, we have dA over dt, we have B, and we have C. The one thing that we don't have is dC over dt. But that's not hard to figure out because this is a ladder and it's leaning against a wall. So the ladder size is not going to change. And if the size isn't changing, that means that we can assume safely that dC over dt is 0. The rate of change is 0. So I'm going to go plug all this in. So I would have 2 times 15 times 2 plus 2 times 20 times the unknown, which is dB over dt, equals 2 times 25 times 0. So that tells me that 60 plus 40 dB over dt is equal to 0, which tells me that dB over dt is equal to negative 60 over 40, or negative 1.5 feet per second. Now this shouldn't be a surprise to you that this is negative, because if you take a look at it, this length right here should be shrinking because the ladder's falling down the wall. So it makes sense that that would be a negative answer. Now another type of situation that you might see in a related rate problem is something similar to this. So this says a man 6 feet tall walks at a rate of 5 feet per second away from a light that is 15 feet above the ground. And they show you the picture here. And when you look at this picture, you automatically see the right triangle. So the Pythagorean theorem probably jumps out at you. But that's actually not going to help you with this problem in particular. What actually is going on here is that we've set up a similar triangle situation. So you can see that you've got the small triangle here formed by the man and the point where his shadow is, and you've got the larger triangle formed here by the light post and the point of the shadow. So this is a similar triangle, and we do have sides in proportion here. So let's fill in what we know so far. Just coming over here and redrawing our triangle. Or triangles, I should say. We have that this man is 6 feet tall. This is 15 feet. And we know a little bit more information, or at least we will find some in a second. So part A asked us, when he is 10 feet from the base of the light, at what rate is the tip of his shadow moving? So you have to kind of figure out how you want to set this information up. So we know from the beginning of the problem that he's walking away at a rate of 5 feet per second. So what that rate measures is how quickly this side right here, or this portion right here of the triangle, is growing. So I'm going to let this be x. X is going to be the distance from the pole to the man. Okay? And so that's going to be our variable x. And we know from the problem that dx over dt is 5. Okay, so the distance from the pole to the man is x, and dx over dt is equal to 5. Now, we also want to know what rate the tip of his shadow is moving. So I'm going to let y be equal to the distance from the pole to the tip of the shadow. So that means this portion right here we could call y minus x, because it's the whole distance minus x, and we do know that this is a right triangle here as well. So this first part of this problem says, when he is 10 feet from the base of the light, at what rate is the tip of his shadow moving? So this has given us that x is equal to 10, and we need to find dy over dt, because that's the rate that the shadow is growing. Remember, y is the length from here to the shadow. We want to know at what rate is the tip of the shadow moving. So we're not talking about the d of y minus x. We're talking about dy over dt total, because that's the position of the tip of the shadow. So if you're using as your ratio the small triangle to the large triangle, proportional sides tell us that this side here, 6 over 15, has to correspond to y minus x divided by y, because y is the whole side here. And if I cross multiply, that gives me that 6y equals 15y minus 15x. Or that negative 9y, if I subtract the 15y, is equal to negative 15x. Or I get that y equals 5/3 x. So this is going to be my equation for this problem. So now what I have to do is take the derivative with respect to t of both sides of it. So d over dt of y equals d over dt of 5/3 x. So this gives me dy over dt, and this gives me 5/3 dx over dt. And of course I want the dy over dt, and I know that dx over dt is equal to 5 from the original problem. So that tells me that the answer here is 25/3 feet per second. So the second question asks me, when he is 10 feet from the base of the light, at what rate is the length of his shadow changing? So going back to our picture, we can see that this red portion right here is actually the length of the shadow that the man is casting. So the length of the shadow is equal to y minus x. So the rate of the change of the length of the shadow is going to be the derivative with respect to t of y minus x. So that's what we're trying to find, is the derivative with respect to t of y minus x. Now you may look at that and think, oh, I have to set out a different problem and a different proportion, and you could do it that way, or you could use the properties of derivatives. This is going to be the derivative with respect to t of y minus the derivative with respect to t of x, which we know is just dy over dt minus dx over dt. Now in the previous problem, we found dy over dt for when x is equal to 10, and we know from the original information in the problem dx over dt. So this is just going to be 25 thirds minus 5, or 10 thirds feet per second. So we were able to answer that problem using that information. This is an example of a problem that uses the SOHCAHTOA rules in order to find its equation. So we have a triangle here, and you can see from the picture, it says an airplane flies at an altitude of 5 miles towards a point directly over an observer. So we have our observer down here, and our airplane is flying this direction. The speed of the plane is 600 miles per hour. We want to find the rates at which the angle of elevation theta is changing when the angle is A, theta equals 30 degrees, and B, theta equals 60 degrees. So starting off, we know that theta is the angle of elevation, and we do have two different values for theta, but we're going to do the problem in general first and then plug in each value of theta. So what we're trying to find is the rate of the change of the angle of elevation. So we want d theta over dt. Okay, so looking at this triangle, we know that the altitude is constant. That's 5 miles per hour. Okay, and we know that this gap here between these this man and this plane is getting smaller, and it's getting smaller at a rate of 600 miles per hour. So if we let this be y equals 5, and we let this distance here be x equals some number which we don't know yet, we do know that dx over dt is negative 600 miles per hour. We also know dy over dt because the plane is not dipping or rising during its flight. It's going completely at that same altitude the whole time. So dy over dt is equal to 0. Now, if you look with respect to theta, we have information about, or at least variables for, the opposite and the adjacent of sides of this angle theta. So that tells me that I can use the tangent, because tangent of theta is equal to the opposite over the adjacent side, which is part of our SOHCAHTOA rules, and that tells me that tangent of theta is equal to y over x, because that is my variables that I've assigned for that. So when I take the derivative with respect to t of both sides, on the left, the derivative is just secant squared of theta times d theta over dt. And on the right, I'm going to have to use the quotient rule because I've got y over x. So if my f here is y, that's the top, and my g is x, remember these are functions of t, so f prime would be dy over dt, and g prime would be dx over dt. So using the quotient rule, low d high minus high d low over low low, we get x times dy over dt minus y times dx over dt divided by x squared. So this is the setup that we're going to be using to solve for d theta over dt for both answers. Now part A wants us to find the value when theta is equal to 30. So for part A, when theta is equal to 30, we know everything except for y and the dx, we know everything except for x and the d theta over dt that we're searching for. So we need to find x, and we're going to do that by knowing that tangent of 30 degrees has to equal 5 over x. So x would be 5 divided by tangent of 30 degrees, and that is going to be 5 divided by 1 over root 3, which is 5 root 3. So, plugging in, I have that secant squared of 30 degrees times the d theta over dt that I want is going to be equal to 5 square root of 3 times the 0, which was dy over dt, minus y equals 5 times dx over dt equals negative 600, divided by 5 square root of 3 squared. And secant of 30 degrees is 2 over the square root of 3, so that's going to be squared times d theta over dt. And when you do the math here, you get that that's equal to 3,000 divided by 75. So this is 4/3 d theta over dt equals 40. And if I multiply by 3/4 to clear the fractions, I get that d theta over dt is equal to 30 degrees per hour. So that is my answer here. Now I'm going to let you attempt on your own finding d theta over dt when theta equals 60 degrees. You'll follow the same basic process I did here. You'll find x for this particular angle, and then you'll plug all the values in to find your d theta over dt. And you can find the work for that shown in the lecture notes, which are printed. It's all done for you right there. So I want you to try this one out. It's very similar.